Hello everyone! In this video, we'll solve some practice problems in probability. I have a tutorial video on probability. If you want to review the basic concepts, please watch that tutorial before working through these problems. For the practice problems, I'll be using Pearson's MyLab, and under the Fair Doctrine Usage Rule, this is my own commentary on their problems, and it is for educational purposes, so it's all good. Let's get started with a simple probability problem, and then I'll do some more difficult problems. For your convenience, I'll break this video into chapters with timestamps so you can skip ahead if you want to. Alright, let's start with simple and joint events. For our first problem, let's look at 4.1.10. This is a simple question. Let's read it. A survey about social media reported that 79% of B2B marketers, B2B is short for business to business, plan to increase their use of social media as compared with 54% of B2C. That's business to consumers. The survey was based on 1,264 B2B marketers and 1,747 B2C marketers. The accompanying table summarizes the results. Complete parts A through D below. Okay, so if you click on this icon, you'll see the contingency table pop up. So the first question is, give an example of a simple event. Now remember, a simple event is an event that is described by one characteristic. A joint event is described by two or more characteristics, so it would have the word "and" in it. So let's take a look and see if you can identify a simple event. Remember, we're starting out with some simple problems now, and then towards the end of this video, I'll do more difficult problems, so feel free to skip ahead if you feel this is too easy for you. So take a look and see if you can identify a simple event. The first choice is a B2C marketer and plans to increase use of social media. So that's a joint event, right? Because that is B2C and plans to increase, so two characteristics. The next choice is a B2C marketer. Well, there's no "and" there, so that's a simple event. The next two choices also have an "and", so the only one here that is a simple event is this one. Fantastic. Okay, here's another question. Give an example of a joint event. And the only choice here that has two characteristics is this one. Is a B2C marketer and doesn't plan to increase use of social media. Okay, that should be easy enough. Next, what is the complement of is a B2B marketer? So the complement is the not, and so is not a B2B, so that would be a B2C marketer. Next, why is B2C and plans to increase use of social media a joint event? Well, obviously, it's because it is describing two characteristics. Let's see what the choices are. The two characteristics are mutually exclusive. Is that true? No, you can be B2C and increase use of social media at the same time, so they are not mutually exclusive. So this answer is incorrect. The next choice is there is more than one way it can happen. No, there is only one way that can happen, so that's not correct. The two characteristics are collectively exhaustive. No, there is also B2B, and there is also not planned to increase use of social media, so it's not collectively exhaustive. And then it is described by more than one characteristic. Yes, that's the definition of a joint event, so that's the answer. Okay, now let's move on to contingency tables. Here we have a contingency table. Do males and females feel more tense or stressed out at work? A survey of employed adults conducted online by a company on behalf of a research organization revealed the data in the contingency table shown to the right. Complete parts A through D below. A, what is the probability that a randomly selected person's gender is female? Okay, so we can open this table up in Excel or do it by hand. Since this is a really simple table, I'm just going to do it by hand, but feel free to open it in Excel and use that instead of a calculator. So what is the probability that a randomly selected person's gender is female? So that would be the number of females, 425, divided by the total, 1025. So using a calculator or Excel if you want, 425 divided by 1025 is 0.4146. But it says to round to 3 decimal places, so it's 0.415, okay? Next, what is the probability that a randomly selected person feels tense or stressed out at work and is female? So, reading off the contingency table, we are looking for the intersection of these two events, and that is yes, feels tense or stressed out at work, and female. So the intersection is 135 people out of 1,025 people. So 135 divided by 1025 is 0.1317. So 3 decimal places is 0.132. Great. Next, what is the probability that a randomly selected person feels tense or stressed out at work or is female? So here we have the union of 2 events, A union B. Remember, and is the intersection of 2 events, but or is the union of 2 events. So let's take a look at the formula. If you remember, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. So in this problem, we want to know the probability of yes or female, right? So that would be the probability of yes plus the probability of female minus the intersection, so minus the probability of the intersection of yes and female. So let's calculate the probability of yes stressed out. Did we calculate that already? No, so let's do that. There are 435 that said yes out of 1025. So 435 divided by 1025 is 0.424390. And what is the probability of a female? We calculated that already. That was 425 divided by 1025. So that's 0.414634. I'm not rounding here because I don't want a rounding error when I put my answer into the MyLab. MyLab is very picky about rounding errors. So keep as many decimal places as you can when you're doing the calculations. And if you're doing the calculations in Excel, you don't have to worry about it since Excel will keep all the decimals for you. So no rounding errors with Excel. So let me write this out. The probability of yes and the probability of female. The probability of female is 425 divided by 1025. That's 0.414634. And the probability of yes is 435 divided by 1025, and that's equal to 0.424390. And next, we need the probability of yes intersection female. So that's 135, right? But it's 135 divided by 1025 divided by the total, and that is 0.131707. So now we have the probability of yes, 0.24390, plus the probability of female, that's 0.414634, minus the intersection of yes and female, so minus 0.131707, and we get 0.707317. So rounding to 3 decimal places, it's 0.707. And nice work. Okay, now let's take a look at another problem, this one using conditional probabilities, and this one is a little harder since they don't give you a contingency table, just a lot of words. You have to construct the contingency table from all these words. So let's take a look. Each year, ratings are compiled concerning the performance of new cars during the first 90 days of use. Suppose that the cars have been categorized according to whether a car needs warranty-related repair, yes or no, and the country in which the company manufacturing a car is based, in some country X or not in country X. Based on the data collected, the probability that the new car needs a warranty repair is 0.06. The probability that the car is manufactured by a company based in country X is 0.5, and the probability that the new car needs a warranty repair and was manufactured by a company based in country X is 0.015. Use this information to answer A through D below. Okay, that's a lot of words, so let's break it down by first constructing a contingency table. There are two variables here. Whether or not the car needs a warranty-related repair, yes or no. So I'll make yes or no the rows. And country of origin, X or not X. So let's call that X prime. That's the complement of X. And that will be the columns. And let's make a column for the totals and a row for the totals. Okay, so now I have the table set up with the rows for warranty-related repair, yes or no, and the columns for the country, either X or X prime. Now, back to the problem. Based on the data collected, the probability that the new car needs a warranty repair is 0.06. So let's put that in the table right here. And the probability that the car is manufactured by a company based in country X is 0.5. So that would go in the column for country X, 0.5. Now, these are probabilities, so probabilities always add up to 1. So let's make this the total, 1. So then I know that this is going to be 0.5 and this is going to be 0.94. I can also put a formula in the cell instead of typing in the number. This would be equal to 1 minus 0.5, and so that gives me 0.5. And this would be equal to 1 minus 0.06, and that gives me 0.94. Okay, so now we have all the marginal probabilities filled in. Let's go back to the problem. There's one more number they gave us, and the probability that the new car needs a warranty repair and was manufactured by a company based in country X is 0.015. Okay, so let's fill that in on Excel. That would be the intersection of yes and X, and that's 0.015. So now we can fill in all the rest of the cells. Since the rows have to add up across to the total and the columns add up down each column, so we can easily find the missing numbers. So for this cell, the row has to add up to 0.06, and to get that missing number, I take 0.06 minus 0.015, and that gives me 0.045. And then we have 0.5 minus 0.015, and we get 0.485. Next, we have 0.5 minus 0.045, and we get 0.455. And you can check to see that everything adds up to the totals across each row and down the columns. And of course, everything altogether adds up to 1. Okay, so now we have the table. We can go back and see what the question is. Suppose you know that a company based in country X manufactured a particular car. What is the probability that the car needs a warranty repair? So this is an example of a conditional probability. We're given the information that the country is X. So given X, what is the probability of yes? We can write that like this: P, the probability of yes, given X. So given country X, what is the probability that yes, the car will need a warranty-related repair? And that is equal to the probability of yes intersection X divided by the probability of X. So the numerator is the intersection of yes and X, and that's 0.015. And the denominator is the probability of the given, so the probability of X, that's 0.5. So 0.015 divided by 0.5 is 0.03. So that's the answer, 0.03. Then we have another part to this question, B. Suppose you know that a company based in country X did not manufacture a particular car. What is the probability that the car needs a warranty repair? Okay, so that's given country X prime. So let's write out the formula first. It's written as P, the probability of, and then in parentheses, yes, given X prime. And that is the probability of yes intersection X prime divided by the given, which is X prime. So that's 0.045 divided by 0.5. And that is 0.09. Great. Next part, C. Our need for warranty repair and location of the company manufacturing the car independent. So we already know that the probability of yes given X is 0.03. So what is the probability of yes without the given information about the country? The probability of yes is 0.06. So is the probability of yes given country X the same as the probability of yes? No. 0.03 is not equal to 0.06, so they are not independent. They are dependent, right? Remember, if the probability of A given B is equal to the probability of A, then they are independent events, right? Because the given information didn't help with the probability. So, but in this case, they are not equal, so they are not independent. So the answer is no, they are not independent. Okay, let's look at a more complicated problem. This one deals with a deck of cards and conditional probabilities. A standard deck of cards is being used to play a game. There are 4 suits, hearts, diamonds, clubs, and spades, each having 13 faces, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king, making a total of 52 cards. This complete deck is thoroughly mixed, and you will receive the first 2 cards from the deck without replacement. Complete parts A through D. All right, part A, what is the probability that both cards are jacks? So let's see how we would solve this. Both cards have to be jack. So remember the formula for A intersection B? The probability of A intersection B is equal to the probability of A given B times the probability of B, which can also be written like this, the probability of B times the probability of A given B. It's the same thing. So now we want to know the probability of both cards being a jack. That would mean the first card has to be a jack, so that's the probability of B, the first card being a jack. And then, given that the first card is a jack, what is the probability that the second card is a jack? Okay, let's start with the first card. What's the probability that the first card will be a jack? Well, how many jacks are there in a deck of cards? 4, right? So the probability that the first card will be a jack is 4 out of 52, right? Now, given that the first card was a jack, what is the probability that the second card will be a jack? So if the first card is a jack and we don't replace it, we don't put it back in the deck, so now there are only 3 jacks left in the deck. And how many cards are left in the deck? Now there are 51 cards left in the deck, right? Because we took out the first jack. So given that the first card was a jack, then the probability that the second card is a jack is 3 out of 51, right? since there are 3 jacks left and only 51 cards left because the problem says 2 cards are taken out without replacement. Replay this to make sure you understand where these numbers come from. So now we have 4 over 52 times 3 over 51, which is 0.076923 times 0.058824, and that is 0.004525. And since my lab wants 4 decimal places for this problem, the answer is 0.0045. Okay, we're not done yet. B, what is the probability that the first card is a 7 and the second card is a 5 or a 6? So let's start with the first card. The probability of the first card being a 7 is 4 out of 52, right? There are 4 7s and 52 total cards, so 4 out of 52. Now, given that the first card is a 7, what is the probability that the second card is a 5 or a 6? Well, how many 5s or 6s are left in the deck? There are 4 5s and there are 4 6s, so there are 8 possible cards left in the deck. And since we already took out the first card, there are 51 cards left. So the probability that the second card is a 5 or a 6, given that the first card was a 7, is 8 out of 51, right? So now let's divide 4 out of 52. We already calculated that. It's 0.076923. And 8 out of 51 is 0.156863. Now let's multiply and we get 0.012066. And my lab wants 4 decimal places, so the answer is 0.0121. Great! Moving on to part C, if you were sampling with replacement, so that means we put the first card back and then select a second card. So if you were sampling with replacement, what would be the answer in A? So the probability of both jacks would be, well, the probability of the first card being a jack is 4 out of 52. And then we put that card back in the deck, so the probability of the second card is also 4 out of 52. So 4 out of 52 times 4 out of 52, or 0.076923 times 0.076923, or squared, and we get 0.005917. So that's 0.0059. Okay, that's great. Next, part D. Okay, this is a tough one. In the game of blackjack, the picture cards Jack, Queen, King count as 10 points, and the ace counts as either a 1 or 11. All the other cards are counted at their face value. Blackjack is achieved if 2 cards total 21 points. What is the probability of getting blackjack in this problem? Okay, so let's see how we can get blackjack. We get 2 cards, the first card and the second card, and they have to add up to 21. So let's see. We can have the first card as an ace, and then the second card can be either a 10, jack, queen, or king, and that will add up to 21. So that's one way we can get blackjack. And then another way we can get blackjack is if the first card is a 10, jack, queen, or king, and the second card is an ace. So we can get blackjack one of these 2 ways. Either the first card is an ace and the second card is a 10, jack, queen, king, or the first card is a 10, jack, queen, king, and the second card is an ace. So those are the 2 ways we can get blackjack. Now let's look at the first way. What is the probability of getting an ace for the first card? So that would be 4 out of 52, right? There are 4 aces in a deck of 52 cards. So 4 out of 52. And then given that the first card was an ace, What is the probability of a 10, Jack, Queen, or King? Well, there are 4 ways for each of those. There are 4 10s, 4 Jacks, 4 Queens, and 4 Kings. So there are 16 cards that can count as a 10. And then there are 51 cards left in the deck since we already took out the first card. So 16 out of 51, right? So that's one way that we can get blackjack. Now the second way of getting blackjack, and we're going to add these 2 ways together. The first card can be a 10, Jack, Queen, or King. So that's 16 out of 52. And then given that the first card was not replaced, the probability that the second card is an ace is 4 out of 51, right? So now let's do the calculations for the first way. 4 out of 52 is, we did that before, 0.076923 times 16 out of 51, that's 0.313725. And multiply that, we get 0.024133. Now for the second way, we have 16 out of 52, that's 0.307692 times 4 out of 51, that's 0.078431. And we get the same answer as before, 0.024133. That's because mathematically we have the same numerators, 4 and 16, and we have the same denominators, 52 and 51, so we get the same answer. And then we add the 2 ways together, so 0.024133 plus 0.024133 is 0.048266. So my lab wants 4 decimal places, and that would be 0.0483. And we're right. Yay! Okay, now let's review some problems using counting rules, and then we'll be done with this review of probability. Here's a problem. There are 16 teams in a high school baseball league. How many different orders of finish are possible for the first 4 positions? So is this a permutation or a combination? Well, does order matter? Yes, it says how many different orders are there. So this is a permutation. We can use the permut formula in Excel, P-E-R-M-U-T. So we have 16 total and then 4 for little n. So using Excel, we can type in equal to, then P-E-R-M-U-T, then in parentheses, the number, that's 16, and then the number chosen. So 16 for the number and 4 for the number chosen. So 16, comma 4, close parentheses, hit enter, and we get 43680. So Excel really excels here. 43680, and that's correct. How about one more problem? Let's take a look at this one. There are 18 bikes in a fitness store, and the fitness store owner wishes to select 4 of them to display. How many ways can a group of 4 be selected? Okay, now is this problem a permutation or a combination? Well, does order matter here? No, so this is a combination problem. We can use the combin function in Excel, that is equal to, then C-O-M-B-I-N, open parentheses, the number, comma, the number chosen, close parentheses, right? So that would be 18, comma 4, and that is 3060. So there are 3060 ways to choose 4 bikes out of 18. And we got it right. Okay, so that was a lot to digest for one video. You might want to review these problems. It will help in understanding basic probability concepts. I hope you enjoyed this video, and as always, I hope you learned something.